Good afternoon, my dear students. Now, in the previous video clip, already have discussed about that is a transformer, the principle of the transformer, construction of the transformer, working of the transformer, and its theory. What is the meaning of step-up transformer? What is the meaning of step-down transformer? All these things are already have explained, discussed about these points. Okay. Now few points about that is the transformer. Once again other points. In a previous video clip, how to take that is a output power. Output power is equal to input power. It means the transformer we consider as an ideal transformer. But usually practically you say that no one transformer is ideal transformer. Practically ಹಾಗಿರ್ಲಿಕ್ಕೆ ಸಾಧ್ಯನೇ ಇಲ್ಲ ಅಂದ್ರೆ no one transformer is ideal transformer. Ideal transformer it means it is having 100% efficiency. Once 100% efficiency it means output power is equal to input power. ಈ ತರ ಇರೋ ಸಾಧ್ಯತೆ ಬಹಳ ಕಡಿಮೆ ಇರೋದೇ ಇಲ್ಲ. No one transformer is ideal transformer. ಅಂದ್ರೆ ಎಷ್ಟಾದ್ರೂ ಲಾಸ್ ಎನರ್ಜಿ ಲಾಸ್ ಆಗೇ ಆಗುತ್ತೆ. ಏನೇನು ಲಾಸ್ ಆಗುತ್ತೆ ಇಲ್ಲಿ 4 ಪಾಯಿಂಟ್ ಅದಾವ, ನಾವು ಇಂಪಾರ್ಟೆಂಟ್ ಡಿಸ್ಕಸ್ ಮಾಡೋಣ ನೆಕ್ಸ್ಟ್. ನೋ ಟರ್ನ್ಸ್ ರೇಷಿಯೋ ಇನ್ ಎನಿ ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ ದಟ್ ಯು ಡಿಫೈನ್ ದ ಟರ್ನ್ಸ್ ರೇಷಿಯೋ. Turns ratio is nothing but it is the ratio of number of turns in the secondary to the number of turns in the primary. This is called turns ratio. Each and every transformer having the turns ratio. Turns ratio it means T is greater than 1, Ns is greater than Np. Now Ns is greater than Np it means step up transformer. If T is less than 1 at that time Ns is less than Np. It is in the case of step down transformer. T is greater than 1 for step up transformer. T is less than 1 for step down transformer. This is said to be turns ratio. Turns ratio of the transformer is nothing but the ratio of the number of turns in the secondary coil to the number of turns in the primary. Then you come to the efficiency of the transformer. The efficiency of the transformer is defined as the ratio of output power to the input power. The ratio of the output power of the transformer to the input power, this is called efficiency. Output power, voltage in the secondary into current in the secondary, output power. Input power, voltage in the primary into voltage current in the primary. Now for any transformer, either it is eta efficiency is less than 1 or eta is equal to 1. Eta is equal to, it means the efficiency is 100%. No one transformer is 100%, but efficiency is 1 is nothing but transformer is ideal transformer, but no one transformer is having there is a 100% efficiency. No, the no one transformer is having 100% efficiency, but theoretically you say, practically it is impossible. Okay, but it is less than 1. Okay, no, so efficiency is 90%, remaining 10%. What is this one? Why, where it go? That 10% efficiency. 10% efficiency, it is due to the loss of energy. It is loss, it is very, very important. Loss of energy or power in the transformer. There are mainly important point, 4 points. Ask in the examination. Any 2 points, you write any 2 points, you got 2 marks. 3 marks. One is hysteresis loss and loss due to the leakage of magnetic flux, loss due to the heat or resistance, that is said to be copper loss, and loss due to the eddy currents. Already you know that is eddy current. No, hysteresis loss. During that is transfer the voltage from input to output, it is AC. AC means there is a variation takes place. Current is varies sinusoidally or said to be simple harmonically or periodically. Once current is varies, there is a variation of the magnetic flux. Once variation of the magnetic flux takes place, the there is the core of the transformer is magnetize and demagnetize. During magnetize and demagnetize, there is a loss of energy. That loss of energy in the form of heat, that is due to the hysteresis loss. During transfer the voltage from low input to high output, or high input to low input, at that time magnetize and demagnetize the core of the transformer. At that time there is a loss. That loss is said to be hysteresis loss. How you minimize this one? By using low hysteresis loss materials. Now ಏನು ಮಾಡಬೇಕು, ಈ ಐರನ್ ಕೋರ್ ಇದೆಯಲ್ಲ ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ ಒಳಗೆ ಲೋ ಹಿಸ್ಟರಿಸಿಸ್ ಲಾಸ್ ಇರ್ತಕ್ಕಂಥದ್ದನ್ನ ನಾವೇನು ಮಾಡಬೇಕು, ಯೂಸ್ ಮಾಡಬೇಕು. ನೆಕ್ಸ್ಟ್, ಲೀಕೇಜ್ ಆಫ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್. ವಾಟ್ ಎವರ್ ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಇಸ್ ಲಿಂಕ್ಡ್ ವಿತ್ ದ ಪ್ರೈಮರಿ ಕಾಯಿಲ್, ಆಲ್ ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಈಸ್ ನಾಟ್ ಲಿಂಕ್ಡ್ ವಿತ್ ದ ಸೆಕೆಂಡರಿ ಕಾಯಿಲ್. ಕೆಲವೊಂದಿಷ್ಟು ಕಂಪ್ಲೀಟ್ 100% ಲಿಂಕ್ ಇರಲ್ಲ. ಓಕೆ, at that time there is a loss of energy, loss of power. At that time, to avoid or minimize this leakage of magnetic flux, loss of energy due to the leakage of magnetic flux, how you minimize? One of the coil is wound on another one, like this. ಈ ಥರ ನಾವು ಒಂದು ಕಾಯಿಲ್ ಮೇಲೆ ಇನ್ನೊಂದು ಕಾಯಿಲ್ ವೈಂಡಿಂಗ್ ಮಾಡೋದ್ರಿಂದ ಏನು ಮಾಡ್ಬೋದು, ಲೀಕೇಜ್ ಲಾಸ್ ಡ್ಯೂ ಟು ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಲೀಕೇಜ್ ಆಫ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಏನು ಮಾಡ್ಲಿಕ್ಕೆ ಬರುತ್ತಾ, ಅವಾಯ್ಡ್ ಮಾಡ್ಲಿಕ್ಕೆ ಬರುತ್ತಾ, ಮಿನಿಮೈಸ್ ಮಾಡ್ಲಿಕ್ಕೆ ಬರುತ್ತಾ. ದೆನ್ ಲಾಸ್ ಡ್ಯೂ ಟು ದ ಹೀಟ್. ಇಟ್ ಮೀನ್ಸ್ ಯಾವಾಗಲೂ ಕಾಯಿಲ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ಇದ್ದೇ ಇರುತ್ತೆ. ಇದು ಈ ಕಾಯಿಲ್ಗೆ ಇರುತ್ತೆ, ಈ ಕಾಯಿಲ್. ಒನ್ಸ್ ಯು ಕರೆಂಟ್ ಫ್ಲೋ ಥ್ರೂ ದ ಕಾಯಿಲ್ ಹ್ಯಾವಿಂಗ್ ಸರ್ಟನ್ ರೆಸಿಸ್ಟೆನ್ಸ್, ಒನ್ಸ್ ಇಟ್ ಇಸ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ಇಟ್ ಅಪೋಸ್ ದ ಫ್ಲೋ ಆಫ್ ಕರೆಂಟ್. ಒನ್ಸ್ ಅಪೋಸ್ ದ ಲಾ ಆಫ್ ಕರೆಂಟ್, ನೌ ಇಟ್ ಈಸ್ ಹೀಟೆಡ್ ಅಪ್. ದಟ್ ಈಸ್ said to be copper loss. Due to produce the heat of the coil, due to the flow of current inside the coil in the primary or said to be secondary, there is a loss of energy due to the heat. This this is said to be resistance loss or said to be copper loss. Now power is equal to I square R. How you minimize this loss of power? ಇದು ಕಡಿಮೆ ಆಗಬೇಕಾದ್ರೆ ಏನು ಮಾಡಬೇಕು, ಆರ್ ಕಡಿಮೆ ಆಗಬೇಕು. ಆರ್ ಕಡಿಮೆ ಆಗ್ಬೇಕಂತಂದ್ರೆ ಏನು ಮಾಡಬೇಕು, ಎ ಇನ್ಕ್ರೀಸ್ ಮಾಡಬೇಕು. ಎ ಇನ್ಕ್ರೀಸ್ ಮಾಡ್ಬೇಕಂದ್ರೆ ಕ್ರಾಸ್ ಸೆಕ್ಷನ್ ಏರಿಯಾ. ಒನ್ಸ್ ಯು ಇನ್ಕ್ರೀಸ್ ದ ಕ್ರಾಸ್ ಸೆಕ್ಷನ್ ಏರಿಯಾ, that is said to be thick wire. You using the primary and secondary coil by using the thick copper wire to at that time you minimize the that is the loss of heat, loss due to the heat. ನಾವೇನು ಮಾಡ್ಲಿಕ್ಕೆ ಬರುತ್ತೆ, ಮಿನಿಮೈಸ್ ಮಾಡ್ಲಿಕ್ಕೆ ಬರುತ್ತೆ. ಹೆಂಗೆ ಮಿನಿಮೈಸ್ ಮಾಡ್ಬೋದು, ಥಿಕ್ ಕಾಪರ್ ವೈರ್ ಯೂಸ್ ಮಾಡೋದ್ರಿಂದ ನಾವೇನು ಮಾಡ್ಬೋದು, ಡ್ಯೂ ಟು ದ ಹೀಟ್ ಲಾಸ್ ಆಗ್ತಕ್ಕಂಥದ್ದನ್ನ ಕಡಿಮೆ ಮಾಡ್ಬೋದು. ಲಾಸ್ ಡ್ಯೂ ಟು ದ ಎಡ್ಡಿ ಕರೆಂಟ್ಸ್. ಫೋರ್ತ್ ಪಾಯಿಂಟ್ ಈಸ್ loss due to the eddy current. Once that alternating current is varies, no alternating voltage is also varies. Now EMF is varies. Once EMF is varies, there is a change in the magnetic flux. One change in the magnetic flux, the eddy currents are developed inside the core of the transformer. How you avoid the eddy current loss? Henga avoid ಮಾಡ್ತೀರಿ? Now the bulk iron core is cut into number of pieces or equal pieces of equal thickness and they laminated. Again you pack it. It means the iron of the core is by using the laminated iron core, laminated iron sheets, at that time you minimize the loss of energy due to the eddy current. These are the very four important points. There is the why the power is lost, energy is lost in the transformer. This is important. That is the 4 points. You mention or you write these points, you got the marks. If you ask the two question, 2 points, you write the 2 points, you got the 2 marks. One is hysteresis loss, loss due to the leakage of magnetic flux, loss due to the heat in the resistance or said to be copper loss, and loss due to the eddy current. This is the 4 important reason. And how to minimize, already I explained in previous few minutes, and how you minimize this one, how you minimize the hysteresis loss, how you minimize the leakage of magnetic flux due to the magnetic flux, how you minimize the loss of energy due to the resistance, how you minimize the loss of energy due to the eddy current. Okay, these are very important points. It is the last points in the alternating chapter. Okay, thank you. Good morning, dear students. Now today I discuss about, that is, electromagnetic wave chapter. That is in your syllabus. That is the 8th chapter. This is said to be 8th chapter. It means last chapter in the first part of your book. Before going to that electromagnetic waves, what about the displacement current? That I have to discuss here first. How you got the displacement current? How you recognize? How you find out? How it is discovered? Practically, how you got that displacement? That point out. Now already you know that is the Ampere circuit law in previous chapter. That is the line integral over the magnetic field over any circular closed path is equal to epsilon naught times of the current threaded over that surface and the current flow through the conductor. That point is already, you know, that Ampere circuit law. There is the Ampere circuit law, line integral over. That is the magnetic field around any closed path or loop is equal to epsilon naught times of the current threaded over that surface of the loop. Now see here, it is one important particular that is a experimental method conducted by, that is the Maxwell's. What is that one? Now see here. Now the P and Q are the two parallel plates of the capacitor. Now this is the resistance is connected in series with two capacitors and battery. Now what happens? Now current I is flow through that resistance. Now the electrons are removed here. Electrons are removed. Electrons are collected in the plate Q. What happens? Remove that charge. Electrons, now it gets positively charged. Now electrons are collected here. At that time, that what happens? The plate Q is negatively charged. There is a electric field is exists between the two plates of the capacitor. After a certain time, stop the flow of electrons. It means that capacitor is fully charged or completely it is a charge. Now what happens? You remove this one. You remove this battery. Now you short that circuit with the help of this, the resistance. What happens? Now at that time, the electrons are flow like this. Electrons are flow like this, reverse in the reverse direction. Now current is also flow in the reverse direction. Now this is the, in first previous case, electron flow in this direction. Current is always flow opposite to the flow of electrons. That concept is already, you know, this one. When this is said to be charging, here the capacitor is said to be charging. Here the capacitor is said to be discharging. Capacitor is said to be discharging. Discharge agutta. Discharge agutta. Again there is the electric field. Electric field is go on decreases. Here electric field is go on increases. In electric field increase agutta. Discharge aguva electric field decrease agutta. Now you come to the point. During charging and discharging, you take the closed loop here. I am martani. On the closed loop togotane. Avagillantu current flow agate anta heleno. No, you apply the Ampere circuit law for the surface S1 and for the surface S2. ಇಲ್ಲೇನು ವಿಚಾರ, ಇಲ್ಲಿ ಯಾವುದು ಕಂಡಕ್ಟರ್ ಇಲ್ಲ, ಏರ್ ಇರ್ತತಿ ಅಥವಾ ಏನೋ ಮೀಡಿಯಂ ಇರ್ತತಿ. ಏರ್ ಮೀಡಿಯಂ ಐತಿ ಅಂದ್ರೆ ದೇರ್ ಇಸ್ ನೋ ಕರೆಂಟ್ ಅಂತ ನಮ್ಮ ಕಲ್ಪನೆ. ಇಲ್ಲಿ ಏನು ವೈರ್ ಇಲ್ಲ, ಏನಿಲ್ಲ, ಯಾವ್ದು ಏರ್ ಇರ್ತತಿ ಅಥವಾ ಯಾವುದೋ ಒಂದು ಮೀಡಿಯಂ ಇರ್ತತಿ, ಇಲ್ಲಿ ಕರೆಂಟ್ ಇರೋದಿಲ್ಲ ಅಂತ ಯಾರು ಆಂಪಿಯರ್ ಸರ್ಕ್ಯೂಟ್ ಕಲ್ಪನೆ. ಏನ್ ಹೇಳ್ತಾ ನೋಡ್ರೆ, the Ampere circuit law he applied for this surface S1. Then what you got? This is the current flow through this one. At that time, line integral over this magnetic field over this closed surface S1 is equal to mu naught times of the current threaded over this surface. This is the Ampere circuit law. Now for surface S2, what happens? For surface S2, according to amperes. When you apply the Ampere circuit law for the S2 surface, at that time there is no current at all. He says that there is no current at all. At that time this current is zero. Totally the line integral over this magnetic field between the two plates of the capacitor, you say that is zero. But Maxwell's during charging and discharging, ಏನು ಮಾಡ್ದ ಅವನು? ಡ್ಯೂರಿಂಗ್ ಚಾರ್ಜಿಂಗ್ ಅಂಡ್ ಡಿಸ್ಚಾರ್ಜಿಂಗ್ ಅವನು ಏನು ಮಾಡ್ದ? ಒಂದು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಕಂಪಾಸ್, ಏನದು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಕಂಪಾಸ್. ಮ್ಯಾಗ್ನೆಟಿಕ್ ಕಂಪಾಸ್ ಅಂದ್ರೆ ಏನು? ಮ್ಯಾಗ್ನೆಟಿಕ್ ಕಂಪಾಸ್ ಅಂದ್ರೆ ಚಿಕ್ಕದು ಮ್ಯಾಗ್ನೆಟಿಕ್ ನೀಡಲ್, ಅದಕ್ಕೆ ಮೇಲೆ ಕೆಳಗಡೆ ಗ್ಲಾಸ್, ಆ ಥರ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಕಂಪಾಸ್ ಅಥವಾ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಸ್ಮಾಲ್ ನೀಡಲ್ ಅಂತ ಹೇಳ್ತಾರೆ. That is, needle is placed between the two plates of the capacitor during charging and discharging. What happens? Now, this magnetic needle will deflect. ಅದು ಏನು ಮಾಡ್ತದೆ? ಮ್ಯಾಗ್ನೆಟಿಕ್ ನೀಡಲ್ ಡಿಫ್ಲೆಕ್ಟ್ ಆಗ್ತದೆ. ಆಂಪಿಯರ್ಸನ್ ಪ್ರಕಾರ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಇರಲ್ಲ, ಬಟ್ ಮ್ಯಾಕ್ಸ್ವೆಲ್ಸ್ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಕಂಡಕ್ಟ್ ಮಾಡಿದಾಗ ಆ ಮ್ಯಾಗ್ನೆಟಿಕ್ ನೀಡಲ್ ಕಂಪಾಸ್ ನೀಡಲ್ ಡಿಫ್ಲೆಕ್ಟ್ ಆಗುತ್ತೆ. He says that there is a magnetic field. During charging and discharging of the capacitor, there is an electric field. Electric field is gone, increases during the charging. Electric field is gone, decreases during the discharging. As well as the magnetic field is also exist between the two plates of the capacitor. Therefore, that magnetic field will deflect. Therefore, another current is between the two plates of the capacitor during charging and discharging of the capacitor. That is a missing current. That is a missing current. That missing current is called displacement current. Oh, ಈ ಕರೆಂಟ್ ಬಿಡೋ ಹಾಗಿಲ್ಲ, ಈ ಕರೆಂಟ್ ನಾವು ತಗೊಳ್ಬೇಕು. ಆ ಕರೆಂಟ್ಗೆ ಅವನೇನಂದ ಸ್ವಲ್ಪ ಡಿಸ್ಪ್ಲೇಸ್ ಆಗೋಗ್ಯದ, ಆ ಕರೆಂಟ್ ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಕರೆಂಟ್ ಅಂದ. ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಕರೆಂಟ್ ಒಮ್ಮೆ ಏನಾಗುತ್ತೋ ಹೆಚ್ಚು ಇರ್ತದೆ, ಕಡಿಮೆ ಇರ್ತದೆ. ಓಕೆ, ಆ ಕರೆಂಟ್ ಮಿಸ್ಸಿಂಗ್ ಕರೆಂಟ್ ಏನಂದ? ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಕರೆಂಟ್ ಅಂದ. ಯಾವಾಗದು? The current which is developed between the two plates of the capacitor during charging and discharging of the capacitor, that current is called displacement current. ಇದು ಡೆಫಿನೇಷನ್ ಆಫ್ ದ ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಕರೆಂಟ್. ಅವಾಗ ಏನು ಹೇಳ್ದ? ಆಂಪಿಯರ್ಸ್ ಮಾಡಿಫಿಕೇಶನ್ ಮಾಡ್ದ. ಏನು ಮಾಡ್ದ? ಮಾಡಿಫೈಡ್ ಇಕ್ವೇಶನ್ ಕೊಟ್ಟ. ಮ್ಯಾಕ್ಸ್ವೆಲ್ಸ್ ಆಂಪಿಯರ್ ಸರ್ಕ್ಯೂಟ್ ಲಾ ಇಕ್ವೇಶನ್ ಅಂದ್ರೆ ಅವಾಗ ಇಲ್ಲಿ ತನಕ ಏನಂದ್ರು? ಆಂಪಿಯರ್ ಸರ್ಕ್ಯೂಟ್ ಲಾ ಇಕ್ವೇಶನ್ ಅಂದ್ರು. ಇಲ್ಲಿ ಮುಂದೆ ಏನಾಗ್ತದ? ಮಾಡಿಫಿಕೇಶನ್ ಆದ್ಮೇಲೆ ಆಂಪಿಯರ್ ಸರ್ಕ್ಯೂಟ್ ಲಾ ಅಂತಂದ್ರು. ಹಾಗಾದ್ರೆ ಟೋಟಲ್ ಕರೆಂಟ್ ಓವರ್ ದಿಸ್ ಕ್ಲೋಸ್ಡ್ ಲೂಪ್ ದಟ್ I is equal to IC plus ID. ಹಂಗಾರೆ IC ಅಂದ್ರೆ ಏನು? ಕಂಡಕ್ಷನ್ ಕರೆಂಟು. ಹಂಗಾರೆ ID ಅಂದ್ರೆ ಏನು? ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಕರೆಂಟು. ಇದು ಕಂಡಕ್ಷನ್ ಕರೆಂಟು, ಇದು ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಕರೆಂಟು. ಎರಡು ಕರೆಂಟ್ ಹೇಳ, ಎರಡು ಕರೆಂಟ್ ತಗೋಬೇಕು. ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಕರೆಂಟ್ ಬಿಡೋ ಹಾಗಿಲ್ಲ ಅಕಾರ್ಡಿಂಗ್ ಟು ಮ್ಯಾಕ್ಸ್ವೆಲ್ಸ್. ಅವಾಗ ಟೋಟಲ್ ಕರೆಂಟ್ ಈಸ್ ಕಂಡಕ್ಷನ್ ಕರೆಂಟ್ ಅಂಡ್ ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಕರೆಂಟ್. ಆ ಕ್ಲೋಸ್ಡ್ ಲೂಪ್ ನಾಗ ನಾವೇನು ಮಾಡಬೇಕು? ಇಲ್ಲೇ ಎರಡೂ ಕರೆಂಟ್ ತಗೋಬೇಕು. ಕಂಡಕ್ಷನ್ ಕರೆಂಟ್ ತಗೋಬೇಕು, ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಕರೆಂಟ್ ತಗೋಬೇಕು. ಹಾಗಾದ್ರೆ ಮ್ಯಾಕ್ಸ್ವೆಲ್ಸ್ ಆಂಪಿಯರ್ ಸರ್ಕ್ಯೂಟ್ ಲಾ ಈಕ್ವೇಶನ್, ಇದು ಬರೀ ಆಂಪಿಯರ್ ಸರ್ಕ್ಯೂಟ್ ಲಾ ಈಕ್ವೇಶನ್. ಮ್ಯಾಕ್ಸ್ವೆಲ್ಸ್ ಆಂಪಿಯರ್ ಸರ್ಕ್ಯೂಟ್ ಲಾ ಈಕ್ವೇಶನ್ ಏನಾಯ್ತು? ಲೈನ್ ಇಂಟರ್ವಲ್ ಓವರ್ ವೆಕ್ಟರ್ B dot vector dl is equal to mu naught times of this current is total current is IC plus ID for this closed loop. Againatu IC plus ID. What is the expression for the displacement current? Now expression for the displacement current, epsilon naught into d pi E divided by dt. d pi is change in the electric flux. Now d pi E divided by dt, this is you said to be rate of change of electric flux. ಇದಕ್ಕೆ ನಾವೇನಂತೀವಿ? ರೇಟ್ ಆಫ್ ಚೇಂಜ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಿಕ್ ಫ್ಲಕ್ಸ್ ಅಂತ ಹೇಳ್ತಾರೆ. ಈ ಎಲೆಕ್ಟ್ರಿಕ್ ಫ್ಲಕ್ಸ್ ಚೇಂಜ್ ಆಗೋದ್ರಿಂದ, ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಚೇಂಜ್ ಆಗೋದ್ರಿಂದ ಈ ಕರೆಂಟ್ ಡೆವಲಪ್ ಆಗತ್ತೆ. ಅದಕ್ಕೆ ನಾವು ಹೇಳ್ತೀವಿ ದ ಕರೆಂಟ್ ವಿಚ್ ಇಸ್ ಡೆವಲಪ್ಡ್ ಇನ್ ದ ಟೂ plates of the capacitor during and charging and discharging of the capacitor, its main source is rate of change of electric flux. Therefore, the expression for this is a very important expression. This one, okay. It is asked in the examination. You write the expression for the displacement current. Explain the terms. At that time, you write this expression, displacement current expression. This is the displacement current. Now, suppose you ask the question Maxwell's modified ampere circuit law equation. At that time, integral over vector B dot vector dl mu naught into bracket IC plus epsilon naught d pi E divided by dt, or integral over vector B dot vector dl is equal to mu naught IC conduction current plus mu naught epsilon naught d pi E divided by dt. This is about the explanation about the displacement current and ampere's modified that is Maxwell's modified ampere circuit law equation. That is a very important concept. And then you follow this video clip repeatedly, then only you clearly understand this one, and also you follow the notes. Thank you.